We're asked to compute the matrix exponential e to the power of ta, where matrix A is the 3 by 3 matrix with entries 1, -3, 2 in the first row, -2, 1, 2 in the second row, and -1, -3, 4 in the third row. And then we're also asked to find the general solution to x prime equals a times t. We begin by determining the eigenvalues and corresponding eigenvectors for matrix A. If matrix A has 3 linearly independent eigenvectors, because matrix A is a 3 by 3 matrix, then we follow the general procedure outlined on the right to determine e to the power of ta. Let's first find the eigenvalues by setting up the equation, the determinant of the difference of a and lambda I equals 0, and then solving for lambda. So here we have the setup. Next we simplify, then we evaluate the 3 by 3 determinant. You can see from the work here I use row 1. You may want to pause the video and verify this setup. Next we evaluate the 2 by 2 determinants, simplify, factor, set equal to 0, and solve, which I've done here. Notice we have 3 eigenvalues. We have lambda sub 1 equals 3, lambda sub 2 equals 2, and lambda sub 3 equals 1. The next step is to determine the corresponding eigenvectors. To do this, we set up the equation, the difference of a and lambda I times vector v equals a 0 vector, then determine a vector v. We do this for each of the 3 eigenvalues. Going to the next slide, we begin with lambda sub 1 equals 3. Here's the setup. Again, we have the difference of matrix A and 3 times the 3 by 3 identity matrix times vector v equals a 0 vector. Next we simplify, and now we need to solve the system. I'm going to go ahead and use an augmented matrix and write it in reduced row echelon form. Notice v3 is a free variable. Row 1 indicates that v1 equals v3. Row 2 indicates v2 equals 0. If we let v3 equal 1, we have the eigenvector v1 is the vector 1, 0, 1. And now we do the same for lambda sub 2 equals 2 and lambda sub 3 equals 1. I'm not going to show that work here due to time. For lambda sub 2 equals 2, we have a corresponding eigenvector 4, 2, 5. And for the eigenvalue lambda sub 3 equals 1, we have a corresponding eigenvector 3, 2, 3. Because matrix A is a 3 by 3 matrix, and we have 3 linearly independent eigenvectors, to find the matrix exponential, we follow the procedure above, where step 1 we write matrix A in the form of E, D, E inverse, where D is the diagonal matrix with the eigenvalues along the main diagonal, and E is the matrix formed using the eigenvectors as the columns. Let's go ahead and set up step 1 using the eigenvalues and corresponding eigenvectors. We have the given matrix A is equal to the first matrix is matrix E, where the columns are the eigenvectors. Notice the first column is 1, 0, 1. The second column is 4, 2, 5. The third column is 3, 2, 3. Then we have times matrix D, where matrix D is a diagonal matrix with the eigenvalues of 3, 2, 1 along the main diagonal. Then we have times E inverse. Now that we have this equation, if we go back to our notes in blue, if we exponentiate both sides of the equation with the base of E, in our lesson, we proved that e to the power of e d e inverse is equal to e times the exponential e to the d times e inverse, which gives us the equation e to the a equals e times e to the d times e inverse. If we include a factor of t, we get the formula below that we use to determine the matrix exponential e to the power of ta. E to the ta is equal to e times e to the td times e inverse. So for step 2, the exponential e to the power of ta is equal to matrix E, and then the exponential e to the power of td, because matrix E is a diagonal matrix, is also a diagonal matrix where along the main diagonal we have e to the 3t, e to the 2t, and e to the t, with all their entries at 0. And then we have times e inverse, which I've already found here. To find e inverse by hand, we can use an augmented matrix where we have matrix E in the first 3 columns, and the 3 by 3 identity matrix in the second 3 columns, and then perform row operations so that we have the 3 by 3 identity matrix on the left and the 3 columns on the right give us E inverse. And now we simply multiply to determine the exponential e to the power of ta. So here I've broken this up in steps. Here I've multiplied the first 2 matrices, and then we take this result and multiply by the third matrix, which results in the matrix exponential e to the power of ta, shown here on the right. Because I didn't show the multiplication, you may want to pause the video and verify all this is correct. But this is the matrix exponential e to the power of ta. And now for the second part, we're asked to determine the general solution to x prime equals a times x. Let's do this on the next slide. Since the exponential is a fundamental matrix solution such that e to the power of 0a equals the identity matrix at t equals 0, the general solution is x equals e to the power of ta, the matrix exponential, times c, where c is a constant vector. And therefore the general solution is x equals, again, the matrix exponential e to the power of ta times the vector c, which is the vector c1, c2, c3. This is the general solution. I hope you found this helpful.